So yeah, I'm going to be talking about modelling or how we can predict Atlantic salmon population dynamics. So a bit of a different spin. I'm just going to grab this. So we all know here, and we've all seen, that Atlantic salmon are declining. But if we want to be able to predict what's going to happen to them, we need to be able to understand the mechanisms, so the processes that are driving interactions. So the benefit of this being that a more mechanistic model, which can tell you about the processes that are driving patterns, can then extrapolate beyond the observed conditions. So, for example, you can look what's happening in more novel scenarios. So these are more grounded in how things actually work, which makes them harder to get right, but once you do get them right, they can deal with these new scenarios. So this is compared to more classical statistical models, which basically fit a model that best describes the data that you have. So not only does this need a lot of data, it doesn't have the same predictive power, so you don't have the same capacity. So these models may work if your current conditions don't change. So for example, it might seem to work, but we all know that that's not going to be the case. So for example, with climate change. And these statistical models are currently what most Atlantic salmon population models are based upon. So how can we model our salmon more mechanistically? Well, the key mechanism for Atlantic salmon all evolves around the life cycle. So how well your population does, so its growth or decline, depends on things like how you live, how you grow, how you feed, how you die, how you reproduce. And this sort of complexity also varies across populations. So, for example, the time that you remain as a par can vary between 1 to 7 years. So it's 7 years as a par in the river up here in Iceland. And as well as this, these life stages also have a phenological timing. So it's clear, and we've seen some other talks, that temperature is a really important factor that's driving the dynamics of these systems. And this is because that they're ectotherms, so they're cold-blooded species, where basically your environmental temperature determines your internal chemical reactions. So we can therefore mechanistically model the life cycle in the same way. So we've got a size-based, temperature-dependent model, which we term a metabolic integral projection model, which if you want to know a bit more about later, you can come and chat to me. But basically, in the same way that we saw with our life cycle, we have temperature that drives our vital rates of growth, survival, and reproduction. So then what this mechanistic modeling approach can allow us to do is summarize all this complexity that we see in the life cycle into just one measure. And we term this population fitness, which in ecology we give this Greek symbol lambda to. And if you remember during COVID, where you have your R0 number, which basically tells you how well COVID was spreading through your population, lambda works in the same way. So if you have a lambda greater than 1, it can say that your population's increasing, it's growing. If you have a lambda of less than 1, then your population's declining. So now we have our population model. We can look at this population fitness across a range of temperatures. So we've got our population fitness on the y-axis and then increasing temperature on the x-axis. And then we can see the grey dotted line is basically where lambda's equal to 1. So your population's stable, it's neither growing nor declining. Then above this, your population fitness is increasing. Below this, your population fitness is declining. And then we've looked at this for 2 temperature modeling regimes. So basically a fixed mean temperature model, which is the solid line, as well as seasonal fluctuations, which is the dotted line. And we'd also expect these fluctuations to increase under climate change. And then we've also compared it for 2 levels of growth. So the yellow is under optimal growth, so it's like unlimited resources. And then we've got a more restricted growth, so it would be less resources available, which is more like what we'd expect to see in the real world. And we can basically see here that we have a thermal performance curve with temperature. So your population fitness starts to increase, and this is because your individual growth rates increase as it gets warmer. And then this reaches a thermal optimum, where temperatures above this are now detrimental and your fitness decreases. And that's basically because at these higher temperatures, your mortality is higher. And then this is also shown with the fluctuating temperature regime, where basically as you reach these more lethal temperatures, more frequently your population fitness declines at a faster rate. And then we can also see that under the lower growth scenario, so this is like having less food, that basically your fitness is reduced overall across the whole temperature range. And this is basically because warmer systems are faster. So if it's warmer, you can grow faster, but if you don't have the food to support that, then your fitness is going to be affected. And what's really cool about this is that our model's able to predict these thermal limits to our populations. So This is a mechanistic model built from first principles, and we can see the fundamental thermal niche of salmon. So this is like where salmon are actually found, the mean annual temperature range where they're found. And without the model even knowing this, we can see that outside of this range, your fitness is impacted. And this is really cool because it's predicting this independently and it works. And so we can then use the model to look at what will happen in the future for populations under warming. So now what about our data? So we've got the range of salmon shown in the dark blue, and then locations of our rivers up here in Iceland, which you've already seen. And we can see that these are all pretty cold rivers as far as it goes for salmon. So we can also compare this to rivers from across its range. So we do this because not only does it span such a large range, these populations, but also what's happening in more warmer rivers could also be indicative of what's happening in our cold rivers under warming. So this gives us two temperature regimes, cold versus warm. And then we can look at the data from these locations. So this is from electrofishing data. These are juvenile size distributions. And we can basically see that they're differing between the locations. So now this size-based data can be used in our size-based temperature-dependent model, and we can look at if temperature is driving these differences or if it might be down to something else. So, for example, if we remember our model, we've got temperature varying in these systems, but we can also vary our growth rates and our survival rates, which we can see on the axes of this graph, to see if something else is driving them. So, for example, increasing growth rates could be like varying resources, so different productivities of systems. So if only temperature was driving differences, we'd expect all our different locations to appear on the same parameter space on this graph. So what do we find? So they're all sort of clustered in the same sort of area, our different rivers, and we can see these two guys stick out as having a higher individual growth rate. And if you look at the ecology of these rivers, this also comes out. So, for example, the Hofsau up here in Iceland is a much larger catchment. It's much more forested compared to the other rivers. And as well as that, Sami's shown that the primary productivity is higher in this system. So the model's picking out that it thinks productivity is essentially going to be higher in this system. And similarly, the Froome, which Rasmus shows, is a well-known productive UK chalk stream. So it's showing not only temperatures driving differences here, but that productivity in these systems is also an important factor, which we can pick out. And then as well as this, the model can then also start to reveal what's happening at other stages, all different sizes at any time of year. So for example, the Vesta-Delta data electrofishing that we looked at is just one subset at one time of year. So sort of below this, you're too small to be electrofished. Bigger than this, it becomes logistically difficult when you go to sea and things like that. However, on the Vesta-Delta, they do have a counter, so we can start to look at adult data and see, sort of reveal more, especially with tagging what's happening, which is great. That's what we need to inform these models. But as well as this, the benefit of having a model that's developed in this way is it can also help to tell you which life stages or times of year may be most valuable to inform your model. So which stages can sort of have a higher sensitivity to the things that you want to happen in your population. And then just to conclude, so we've shown that we can mechanistically predict temperature limits to population fitness, and that food availability was going to worsen the effect because of the warmer systems are faster hypotheses. And then we can also show other stages at other time of years, revealing that sampling may not be able to, as well as when or where would be best to concentrate your sampling. So now we have this framework. Future steps that you can look at is how climate change can affect Atlantic salmon abundance, as well as identify which populations will become more vulnerable. And then also, due to the nature of the model, you can map management techniques straight onto model parameters. So this allows these model management techniques to be optimized, as in where or when or what will be the effect of things such as egg planting or salmon ladders or landscape restoration. And then, as well as this, you can further develop it to incorporate more testable parameters, thinking about trophic interactions, carrying capacities, or even the marine phase. So, yeah, I just want to thank funders, collaborators, and institutes for access to the data. Thank you.
Thanks very much, Olivia.